Stars are the great engines of the universe, right? They light up the cosmos, they forge new elements. They're kind of the whole show. But what happens when these cosmic giants finally run out of fuel? Well, that's what we're here to find out. We're taking a trip into the stellar graveyard to meet the bizarre, extreme, and frankly awesome things they leave behind. It really is the ultimate cosmic question, isn't it? When a star's life is over, it doesn't just, flicker out. No way. It transforms into one of the most extreme objects you can possibly imagine. And what it becomes all depends on one single thing: how massive that star was to begin with.
So on our journey, we're going to meet the three main residents of this cosmic graveyard. You've got your smoldering white dwarfs, the impossibly dense neutron stars, and of course, the infamous black holes. Each one of them tells an absolutely incredible story of physics pushed to its absolute limit.
All right, first stop on our tour. We're looking at the most common fate for a star, the destiny that's waiting for stars pretty much exactly like our own sun. We are talking about white dwarfs, the glowing, super dense embers of a star's former glory.
So what exactly is a white dwarf? Okay, picture this. You take the core of a star like the sun after it's burned through all its fuel. Gravity starts to crush it, squeezing it down and down and down until it hits a wall. But it's not a normal wall, it's a quantum mechanics wall. See, electrons absolutely hate being crammed into the same space. It's a fundamental rule of the universe. That pushback is called electron degeneracy pressure, and it's the only thing holding this star corpse up against total collapse.
And this is where the scale just becomes mind-bending. You're taking an object with the mass of our entire sun, and you are crushing it down into a ball roughly the size of planet Earth. The density is just off the charts. A single teaspoon of white dwarf stuff would weigh several tons here on Earth. It's just wild.
But here's the catch. That quantum pressure can only hold up so much weight. As you pile more and more mass onto a white dwarf, the electrons inside have to move faster and faster to push back against gravity. But there's a cosmic speed limit, right? The speed of light. If a white dwarf gets too heavy, its electrons would have to break that speed limit to stop the collapse, which they can't do. That absolute tipping point is about 1.4 times the mass of our sun. It's called the Chandrasekhar limit, and it is a hard and fast rule.
Okay, so this is where things get, really explosive. If a white dwarf is all by its lonesome, it's just going to cool down and fade away over trillions of years. But if it happens to have a nearby companion star, it can roar back to life in the most violent way you can imagine.
So the white dwarf's incredible gravity acts like a cosmic vampire, literally sucking hydrogen gas off its poor neighbor. This stolen gas doesn't just fall straight on, it swirls around into this super hot glowing disk called an accretion disk. As this material piles up on the white dwarf's surface, the pressure and temperature just build and build and build until, bam! The hydrogen suddenly ignites in a massive runaway fusion reaction. The result? A spectacular blast we call a nova.
Okay, this is super important because people mix these explosions up all the time. In a nova, it's just the stolen gas on the surface that blows up. The white dwarf itself survives, ready to go back for seconds. But if that greedy white dwarf pulls in so much gas that it crosses that 1.4 solar mass limit, the Chandrasekhar limit we just talked about, the whole star detonates. The carbon inside ignites, and the star is completely obliterated. That's a white dwarf supernova, and it's a totally different beast from a nova or even from the supernova of a massive star.
Now, if a star starts its life way more massive than our sun, its death creates something even more insane than a white dwarf. So let's level up. Welcome to the realm of the neutron star.
So when a really massive star goes supernova, the core collapses so violent that it actually crushes protons and electrons together to form neutrons. What you're left with is a ball of pretty much pure neutrons that has more mass than our sun, but it's been crushed down into the size of a city, like maybe 20 kilometers across. This time, it's neutron degeneracy pressure that stops gravity from winning completely.
I mean, think about it for a second. An object that's only the size of a city, trillions and trillions of miles away, and it's not shining like a normal star. How on earth would you even begin to look for that? It sounds impossible. For a long time, these were just a theory. So, how did we find them?
Well, the discovery was a total accident, which is how a lot of great science happens. A graduate student, Jocelyn Bell, was looking at data from a radio telescope, and she found this weirdly regular signal. It was pulsing so perfectly that for a minute they joked it might be aliens, even nicknaming it LGM-1 for Little Green Men. It wasn't aliens, it was the first ever glimpse of a spinning neutron star.
And this is the brilliant explanation for what she saw. The neutron star is spinning incredibly fast. We're talking hundreds of times a second. It's also got a crazy powerful magnetic field that shoots out beams of radiation from its magnetic poles. Now here's the key. The magnetic poles aren't lined up with the spin axis. So as the star spins, those beams sweep across the cosmos, just like the beam from a lighthouse. And if one of those beams happens to flash across the Earth, bloop, our radio telescopes see a pulse, and that's why we call them pulsars.
But what happens when the collapsing core of a star is so massive that not even neutron degeneracy pressure can stop it? Then, my friends, gravity wins. It wins completely. You get the ultimate cosmic object, a black hole.
Okay, let's be really clear about what a black hole is. It doesn't have a hard surface you could stand on. The event horizon is more like a conceptual boundary. It's the line in the sand. It's the precise distance from the center where gravity is so strong that to escape, you'd have to go faster than the speed of light. And since nothing in the universe can go faster than light, well, anything that crosses that line isn't coming back. It's the ultimate point of no return.
And yep, you guessed it. Just like with white dwarfs, there is a limit for neutron stars. If the collapsing core of that supernova is more than about 3 times the mass of our Sun, there is no known force in the entire universe that can stop the collapse. Gravity just takes over, crushing everything down to an infinitely tiny, infinitely dense point, a singularity, and a black hole is born.
Now let's just bust the biggest myth about black holes right now. They do not go around the universe sucking things up like a vacuum cleaner. That's just sci-fi. Gravity is just gravity. Here's a fun thought experiment. If you magically replaced our Sun with a black hole of the exact same mass, the Earth's orbit wouldn't change at all. We'd just, freeze to death in the dark. You only run into trouble when you get really, really close to one.
But if you do get up close, oh boy, things get weird. This is where Einstein's general relativity really kicks in. Space-time itself gets bent and twisted. For you, time would actually slow down compared to someone watching from far away. Light trying to escape gets stretched out and reddened by the gravity. And the tidal forces, the difference in gravity between your head and your feet, would become so extreme they'd literally stretch you into a long, thin noodle. It's a process with the gruesome but accurate nickname of spaghettyification.
So, we've met the residents of the stellar graveyard. But the story doesn't just end with them quietly fading away. Sometimes these cosmic ghosts find each other, and they engage in one last, absolutely cataclysmic dance.
Way back in the 60s, military satellites looking for secret nuclear bomb tests kept detecting these unbelievably powerful flashes of gamma rays coming from deep space. These are gamma ray bursts, and they are, without a doubt, the single most powerful type of explosion in the universe. We now think they are the birth announcements of new black holes, either from a special super powerful kind of supernova or, even more exciting, from the collision of 2 neutron stars.
And this is just spectacular. Imagine 2 objects, each more massive than our Sun, but only the size of a city, spinning around each other hundreds of times per second. As they do, they churn up space-time itself, sending out ripples called gravitational waves. This process radiates away energy, causing them to spiral closer and closer and faster until they smash together in an explosion called a kilonova. This collision is so incredibly violent that it forges many of the heaviest elements in the universe. That's right, the gold and platinum in your jewelry, it was almost certainly created in a collision between 2 dead stars.
Think about it. From the eerie rhythmic pulses of distant neutron stars to literally hearing the echoes of colliding black holes through gravitational waves, we are developing brand new senses to explore this bizarre cosmic graveyard. We're not just looking at the universe anymore, we're listening to it. And as we tune in more and more closely, who knows what other incredible secrets these cosmic ghosts are just waiting to tell us.